Welcome back, Physical Science 20. This is the second part of the waves, PW1. It's PW1.2. So last day we looked at kind of the vocabulary associated with mechanical waves and waves in general. Now we'll look at one aspect of mechanical waves, and that's speed. So I'll describe the nature of the medium used to transfer waves and its relationship to the speed. Solve problems related to speed, frequency, wavelength using the universal wave equation, the period frequency relationship, and a correct number of sig figs. So I think in the last video I said you'd be doing calculations in PW1.1, but of course you don't. We'll do it in this one. And describe how the speed of sound is determined. Okay, so speed. How fast does a wave move? The speed of the pulse is shown in the figure. So that's one quick flick of the wrist here in this spring or slinky. We can see that the wave is moving that way. It can be found the same way as the speed as anything else, such as a moving car. So to figure out speed, of course, of anything, you need to know how far it traveled and how long it took to go that distance. So V is equal to D over T, something you took back way in grade 10 science. So we measure the displacement of, you could pick a point, figure out how far it goes, time how long it takes to go that specific distance, and then you can get speed. The speed of a periodic wave can be found the same way. So for most mechanical waves, both transverse and longitudinal, we see that speed depends upon the medium through which the wave moves. So in a slinky lab, if you have like if you stretch a spring out so it's really tight, you would see that it would move a certain speed, a different speed than if you had it looser, if you came closer together with the spring and it wasn't as tight. In general, the denser the medium, the faster it moves. Just like the tighter the spring, it'll move much quicker than if the spring was loose. The universal wave equation. Imagine you're standing on a dock on a lake so that you're able to observe the passing waves, and assume you have the equipment that allows you to measure distance and time. First, by timing the duration in which crests passed a certain point, you could measure the period of the wave. How many seconds it takes to make one cycle, so from crest to crest. Then you can take a picture of the waveform and measure the wavelength. So again, distance and time. For these measurements, you can calculate the speed using the following. So yes, we talked about V is equal to D over T. So the distance in our case would be looking at, okay, what is one wavelength going to be? So if here is the dock, and here is the water wave. So if you're looking for how long it takes this crest to reach the area here, that would be one wavelength. You could time how many seconds it takes to go one complete cycle. So the distance is measured by a wavelength. The T is measured by a time. And if you look at the next page here, using the fact that frequency is the reciprocal of period, I could substitute that in. So I remember on the previous page I had V equals D over T, but to measure the displacement, I'm measuring a full wavelength. Time is really going to be period, the seconds per cycle. But since T can be represented as 1 over F, T is 1 over F, and of course how you handle this, a fraction over a fraction, invert and multiply, we get something referred to as the universal wave equation, which you should highlight. Okay, so it's really D over T, but of course T is represented by F and D is represented by wavelength. So let's look at a couple of examples here. A sound wave has a frequency of 192 Hertz, so that's F, and travels the length of a football field. So D is 91.4 meters, and that all happens in 0.271 seconds. So I know D, I know T, and I know F. So let's figure out the speed. I know the distance traveled and the time it takes to travel that distance. So 91.4 meters in 0.271 seconds. So that, of course, is going to give me 337.269 meters per second. If I round it off to 3 sigs, 337 meters per second. Okay. B, what is the wavelength of the waves? Well, if I know wavelength and if I know frequency, if I know speed and if I know frequency, I can figure out wavelength by using the universal wave equation. So V equals lambda F. So if I know my speed, and I'm going to use the non-rounded version. And the frequency was 192. So just simply divide each side by 192. Lambda works out to be 1.756609, and lambda, of course, is in meter sticks. Again, round off to 3 sig figs. That's a 6, so that gets bumped up to a 6. 1.76 meter sticks. Okay, C, what is the period? So C, if I know what to figure out period, if I know what frequency is, it's that reciprocal relationship, right? So 1 over, let's see, 192 hertz is the period of these sound waves. So 1 divided by 192, 0.0052083 seconds per cycle. And of course 3 sig figs. Let's see, don't include the zeros. 520, that's an 8. So this gets bumped up to 1. So there's a period, how many seconds it takes to make a complete cycle. And then D, what if the frequency was changed? If the frequency was changed to 442, what would the new wavelength be? And period, if the speed remains the same. So if the speed remains the same, but frequency is changed, I can figure out what the new wavelength is. So again here, the speed, I'm going to use the non-rounded version. If the speed stays the same, but if the frequency gets a little bit larger, 442, as I was told over here, so divide by 442, divide by 442, lambda becomes 0.763052 meters. I'll round it off to 3 sigs again, 0.763 meters, because that's a 0, so it stays the same. And the question also said, okay, what would the new wavelength and period be? So of course, if I know frequency, I can get period. So if the new frequency is 442.00222624 seconds. Again, rounded off to 3 sigs, 0.00226 seconds. Okay, so I have a couple of relationships here, and again, you'll get a reference sheet for these. But again, the relationships we have to figure out the speed of something, distance over time. To figure out, another way to figure out speed is using the universal wave equation, lambda and frequency, if I know that. And of course, from previously, the relationship between frequency and period, depending upon which we're looking for, I have that. So that's how we can figure out the speed of mechanical waves such as water waves, slinky waves, spring waves, string waves. Speed of sound is a little bit different. So the speed of sound, again, we could figure it by distance over time, but it depends upon the temperature. Because if you think about it, to have sound travel, you need vibrating air molecules. And at different temperatures, air molecules vibrate a little bit differently, sometimes faster, sometimes slower. So they depend upon the temperature, with the speed increasing about 0.6 meters per second for every 1 degree C rise in temperature. So we can use the following as that. At 0 degrees, the speed of sound in air is 331 meters per second. But of course, for every 1 degree C, we add 0.6 onto that. So for example, if we're looking at room temperature, 20 degrees C, looking at sound moving, how would that change? So 331 plus 0.6 T. So if we moved up 20 degrees, that's 20 intervals of 1 degree increases. So we take 0.6 times 20, so we get 343 meters per second. Sound also travels through solids and liquids. In general, the speed of sound is greater in solids than in liquids, because again, we said earlier that in denser mediums, the speed of sound is faster. So it moves faster in solids and liquids than it does in gases, which is a lighter medium. Table below right lists speeds of sounds in various media. Sound cannot travel in a vacuum, such as out in space, because, again, to have sound, you need something vibrating, a medium to transmit it. Air molecules. And of course, where there's no air molecules, we won't be able to keep transferring it over. So yes, unfortunately, we would not be able to hear laser and explosions in Star Wars. So we kind of turn a blind eye at this physics rule so that the movie will be more exciting. So if I look over here, air at 0 degrees C, 331. Air at 20, like we just calculated, 343. Helium, 972. Water, seawater, copper, iron. So you can see it increases as we get into a denser medium. Okay, so let's look over here. The temperature outside is 23 degrees C. What is the speed of sound in air at this temperature? So easy, we could just simply use that relationship there. Speed of sound in air is 331 at 0 degrees C, but for every increase in 1 degree C, we add on a 0.6. So if I'm looking at going up from 0 to 23, that's 23 movements. 23 of these 0.6s are going to be added on to that 331. So that gives me 344.8 meters per second. I'll round that off to 3 sigs. 345 meters per second. And on the next page, of course, we could do vice versa here. If we know what the speed of sound is, we could figure out what the temperature we must have had for that to occur by using the same idea here. If we know the speed is 318, I could figure out what temperature it must be outside. So of course, solving to get the t variable, I need to isolate this whole term right over here. So that means I'm going to subtract 331, subtract 331, so 0.6. So this is going to cancel, and over here I'm going to get negative 13, then divided by 0.6, divided by 0.6. T is going to be equal to negative 13 divided by 0.6. Oh, so I end up in the negatives here. And I'll round that off to 3 sig figs. And with that, it works out to be negative 21.7 degrees C. So you can look at it vice versa. All right, so that's it for PW1.2. Should be able to do the assignment. There's some calculations involved there, very similar to what we did here. And we'll see you again.